Question 6.3.2, calculate the maximum length of QT. All right. First things first, when we see the word maximum or minimum in our exams, we must first, and it won't always be this, but we must first think of calculus, and in particular, the derivative of some function and the first derivative test. And what I mean by that is the first derivative test, the derivative of a function. When you set that equal to 0, you find local maxima and minima of functions, so extrema points. That's what we do. That's what happens when you set the derivative of a function equal to 0. And that's useful because that often shows turning points, right? So that implies that our original function is at a maximum or a minimum at the turning points of its derivative. And we can either find local minimum or local maximum. And often we won't need to distinguish, are we finding a maximum or a minimum, because they'll often tell us what we're finding. However, if you're not sure what you are finding, if the derivatives function like this, if it goes from positive to negative in gradient, you're finding a local maximum. If it goes from negative to positive, this is the derivatives functions graph, you're finding a local minimum. And this can pop up in all sorts of places like water flow, and if you have a piece of rope and you're trying to find the biggest rectangle that you can create with a given piece of rope. And so the important thing I just want you to understand is that when you see maximum and minimum, we must think of calculus and the first derivative test. But in order to find the maximum lengths of QT, we first need a function for QT. Oh, but look at that. That's what we've just calculated in our previous question. So let's find the derivative of our QT. So that will be x to the negative half, if I'm correct, minus 8x. And we're now going to set this equal to 0 because we're finding a maximum, a local maximum. Because where a graph changes, remember, where a graph changes in gradient at this point here, f of x is equal to 0. So let's set our function's derivative equal to 0. And now all we're going to do is solve for x. So let's do that. What will that be? 3/2. My arithmetic is failing me here. So all we're doing is solving for x and bringing the one term to the other side, timesing by x to the half to get rid of this x over here. So x will be equal to, let's write it like this, 2/3. There we go. Now let's punch that in our calculator. 1/8, 2/3. I get a quarter. All right, fantastic. Now you might be wondering, okay, what do I do with this? This is where our function is at a local maximum at x equal to a quarter. What we do now is we plug this value back into our QT because we want to find a value for QT, which is the length, where it is at a maximum. And if it is at a maximum at a quarter, let's plug that quarter in. So it was 2 root quarter minus 4 quarter to the 2 plus 6. And let's see if I can do this in my head. How about that? That'll be a half minus 4, 16 plus 6, 1 minus quarter plus 6, and this last little bit I'll do on the calculator. I get 6,75. Now, because we were dealing in the context of a length, we were finding the maximum length between this graph, the green graph and the blue graph. So just to make you understand, what we've done is we found the maximum length between the blue and the green at one of these points over here. That's what we've done. And in particular, its length comes out to 6.75. And because we're dealing with length, what I wanted to say is let's add some context. So we'll put units. 6.75 units. And that is all we had to do. That is the question solved.